All right, welcome to another episode of Science with Zerbeck. Today what we're going to be talking about is an introduction to chemical kinetics and reaction rates. Now before we get underway with the notes, there's a few objectives that I want you to be able to accomplish by the end of this video. Objective number 1, express the rate of a given reaction in terms of the variation in concentration of a reactant or product with time. Objective number 2, calculate the average rate for a reaction over an interval of time given the concentrations of a reactant or product at the beginning and end of that interval. Objective number 3, calculate the instantaneous rates from a graph of reactant or product concentration as a function of time. So let's start out here with a few basic definitions for things that are involved with chemical kinetics. And so we first start out with what our definition is of chemical kinetics. And chemical kinetics is defined as the study of how fast chemical reactions occur. In other words, chemical kinetics is talking about the speed of the chemical reaction. Moving down to this other term here, we have the reaction rate. Now the reaction rate is just defined as the speed at which the chemical reaction occurs. So yes, the chemical kinetics does look at the speed, but specifically the reaction rate. Again, we're talking about a rate, so we're given something per time is the exact definition of that speed of that reaction. There's one more thing that we could add into chemical kinetics here, and that is the reaction mechanism. Now, the reaction mechanism is defined as the exact pathway from reactants to products. Now, with reaction mechanisms, our goal for reaction mechanisms is to understand how chemical reactions occur at the molecular level. Now, with this in mind here about reaction rates and reaction mechanisms, I want to go back up here and add something I should have to chemical kinetics. So chemical kinetics, right, is the study of how fast. This includes the speed of the reaction, and I'm going to add to this and the pathway of how reactants became products. So it's twofold. Yes, the speed, but also the pathway or the reaction mechanism of how reactants became products in a chemical reaction. So both of these things, or all three of these things, are important as we go through this particular unit on chemical kinetics. Now, moving on, we need to figure out, okay, well, we have this baseline definition or definitions of how to describe chemical kinetics. Now we need to understand, well, how or what factors are going to affect that rates of reaction. So the first thing that affects the rate of reactions is the physical state of the reactants. So the state of matter of reactants determines the number of collisions. And so something to remember, something to keep in mind with this, and the reason we bring up collisions is that the more collisions you have when a chemical reaction is occurring, the faster the reaction is going to occur. Now, the other factor that affects our rate of reaction is the concentration of the reactants. And so a rule of thumb here is that increases in concentrations is going to increase the rate of the reaction. Our third factor that affects the rate of reaction is the temperature of the reaction. As the temperature increases, the rate of the reaction increases. And then our fourth and final factor is if we have a catalyst. A catalyst increases the rate of reaction. All right, so we've outlined some basic definition about chemical kinetics. We've also described some of those factors that affect how fast a reaction occurs or the rate of reaction. And now we need to talk about the generalization of that speed of the reaction or the reaction rate itself. And this is important because we're going to do a lot of mathematical operations associated with the speed. So the first thing that we have to remember is this. The speed in our chemical kinetics problems, or in chemical kinetics in general, is defined as the change that occurs per unit time. Now, to help us understand this a little bit better, our units for our speed is molarity per second. And again, as a reminder, the big M stands for molarity. Now, I'll mention this again, but molarity in this case is often written as brackets, and inside those brackets is the molarity of that particular solution. And then, as a reminder, S stands for seconds. All right, so let's go through an example, a very, very generic example, where substance A becomes substance B. So again, these are obviously fictitious substances because substance A is becoming substance B. But let's just say we have this scenario to play out in our head. At time equals 0, or we call that time 0, so before the reaction starts, there is 1.00 molar A, and before the reaction can start, there would be no B present. So again, I'll mention this throughout these notes, but the brackets represent whatever substance we have. That particular molarity goes in these particular brackets. But again, at time 0, your concentration of A is 1 molar and your concentration of B is 0. Now we let the reaction happen, and for this particular reaction, we're going to say at 20 seconds there is 0.54 molar A and there's 0.46 molar B. Notice a couple things. As we lose A, we start to produce B. The other thing to notice here, very, very important, if you add up 0.54 and 0.46 molar, you add that up to the original starting amount that we began with. It's very important to abide by the law of conservation of mass and matter when these examples are going through. Now let's say we let this reaction run, and we let it run to 40 seconds total, and at 40 seconds there is now 0.30 molar A and 0.70 molar B. So again, notice how both of these added together still equal that 1 molar that we began with. And the other thing to notice is this. As we lost more and more A, we produced more and more B. Again, emphasizing here the law of conservation of mass and matter. Now what we can do, and I'm just going to write this in generic terms, but we can talk about the average rate of appearance and the average rate of disappearance. Let's go ahead, let's start with the average rate of appearance of product B. So to find the average appearance of substance B, what you would do, you would find the average rate of appearance by taking the concentration, the change in concentration of B divided by the change of concentration of time. And I'm running out of room here, but for example, if we went from time 0 to time 20 and we wanted to find the average rate of appearance, we would take the change of concentration, so 0.46 minus 0, so 0.46, all divided by the change of time, which was 20 minus 0. And that would get us our average rate of appearance of B during that 20-second time interval. Now what we have here, or what we need to talk about, is the average rate of disappearance of substance A in this particular case. All right, I know I'm running out of room here, but for the average rate of disappearance of A, you would again have the average, you'd have the average rate, and this is equal, the average rate is equal. Very important here because we have this keyword disappearing, meaning, hey, substance A is producing substance B, and thus it is going away. So it would be negative, the change of concentration of A, all, I don't have enough room, but this would be divided by, just like we have on top, the change of concentration of T. So what we would have going on here is this. We would have to take the change of concentration of A, 0.54 minus 1, plug that into our formula, and divide it by the change of time, which in that case there would be 20 seconds. Okay. Now, I'll make that a little bit clearer as we go through our particular sets of problems in the next set or page of notes. Okay, so moving on here, we're going to apply this to an actual reaction here. Now, before we get to that point here, we need to bring up this important note. And that is that reaction rates are determined by monitoring a change in concentration of a reactant or a product. All right, so let's put that information that we just learned to the test. What we have here is our example. This is an organic compound called 1-chlorobutane, and it reacts with liquid water to produce our, that is butanol, and our hydrochloric acid. Now, in an actual lab experiment, these results were obtained in a particular reaction that we see above. Now, notice a couple of key things. One, as the reaction progresses, so as the reaction proceeds in time, notice what happens to the rate. As we go further and further and further into this reaction, the rate of the reaction is going to decrease with time. Again, the average rate is going to decrease with time, and this is because the concentration of reactants are decreasing as well. Again, the average rate is going to decrease with time, and this is occurring because the concentration of the reactants decrease as the reaction proceeds. So it makes sense. Hey, the more and more the reaction goes on, the less and less of the reactants we actually have. And thus, if you're thinking back to what we just learned on the first page of notes, we can think about it like this. The less reactions we have, the less collisions we have, and thus the smaller number of collisions means a slower speed or a slower rate of those reactions. All right, so let's put everything together that we've learned this far. We're going to use this lab data, and the question I'm going to ask is this. What is the average rate of disappearance of our chlorobutane from time at 50 seconds to time at 200 seconds? So I'm going to take a minute. I'm going to write that question down. Okay, so just as a reminder, the average rate formula is the change of concentration divided by the change of time. So for this, we are talking about our compound C4H9Cl or chlorobutane. And so our average rate, I'm just going to write this down, our average rate is going to be the change of concentration of our chlorobutane. So I'm going to put that in brackets because that represents our change of concentration. So C4H9Cl divided by the change in time. Now, what we have, or what we can think about, is this. We have our concentration, okay? And we also have our time. Now, something, as I'm looking at the formula, because this is rate of disappearance, this needs a negative sign out in front. Don't forget about that, because that is very, very important as we progress through that chapter, or this particular unit. Okay, now we need to think about this. The change of concentration is always going to be final minus initial. So we're going to actually start with the portions, or the concentration, at 200 seconds. So we start out with this. The concentration, again, negative, the concentration at 200 seconds for our chlorobutane is 0.0671 molar. And because we put it in brackets, we do not have to worry about putting that M for molarity for a unit. The brackets represent molarity. Now we're going to subtract it from our initial, which our problem said, hey, what happens at 50 seconds? So again, I put this stuff in brackets. I look at 50 seconds, and the concentration at 50 seconds is 0.0905. Again, that is 0.0905 molar. But because we put it in brackets, that represents that is a molarity, so we don't have to worry about that symbol. Now we do the change in time. Well, the problem made it really nice because it said the change in time. So always put your final, which was 200 seconds, minus your initial, which was 50 seconds. Okay? And so we plug this into our calculators. So in this case here, we have to be really, really careful. And we start out here, I'm always going to put that negative sign out in front. So we have negative, the change in concentration, so 0.0671 minus 0.0905. We put that parenthesis there, we divide it by our change in time. Now, whenever you have this type of calculation, ensure you have parentheses, so 200.0 minus 50.0, put that next set of parentheses, and we get an average rate here of 0.00156. Now, to help line this up with the particular chart here, we could put it in scientific notation. So putting it into scientific notation, and we use 3 significant digits, we would get an average rate of 1.56 times 10 to the negative 4th molar per second, or molarity per second. So again, let me write this down here. We would get an average rate of disappearance of 1.56 times 10 to the negative 4th molar per second. Now I kind of squeezed everything here, but that is how we would calculate the average rate. So you take the change in concentration divided by the change in that time, and that's how you'd obtain that value. Again, the answer here is 1.56 times 10 to the negative 4th molarity per second. All right, so now we can move on. We can talk about just another term that is associated with our chemical kinetics. And that term that we have associated is known as our instantaneous rate. Okay, so our instantaneous rate is defined as the rate at any instant in time. So this is saying, hey, at time whatever, what is my rate? Now, how we find this is by using a graph. And so on the graph, it is going to be, the instantaneous rate is going to be the slope of the straight line tangent to the curve at that particular instant you are interested in. Now, it's important to note that this is different than the average rate. All right, so let's go through an example, and I will mention here that, again, the key thing is taking 2 points and subtracting to find that particular instant in time. Okay, so going through this particular problem, we want to calculate the instantaneous rate of disappearance of, again, our chlorobutane at exactly 600 seconds. So what we have here, it's nice, it has this nice little gray area, and what we're going to use is this tangent line to find our particular instantaneous rate right here. So remember, a tangent line is just going to touch this curved line in one spot, and so to be able to find the slope of that particular line, we're going to use these particular points. And we're going to do our best to estimate. And all I'm doing right now is emphasizing where these particular points are. So the first thing that we need to remember is this. Our average rate for the rate of disappearance, because it's disappearance, again, we have to have that negative symbol. And we are going to, how about the instantaneous rate? Should make that correction here. The instantaneous rate, we are going to need the slope. We're going to need the slope of the, our instant rate there of our line here. So for the instantaneous rate, it's going to look very, very similar to the formula that we use for average rate. Just remember, the way that we're getting these values is from that slope of that tangent line. So we're going to take the change of concentration of our chlorobutane divided by the change in time. So we're just going to insert our values here. To save some space, I'll just say our instant rate is this. We have this. I'm going to do my best to estimate our values here, but we're going to start with this particular concentration. And so if you would draw a dotted line all the way over, and again, this is an estimation, but I'm going to estimate that concentration right here to be, let's say 0.017. Now, again, because it's on a graph, your values may vary here, but what we need to do, what we need to ensure is that, hey, this is in brackets to represent, hey, concentration, molarity. Now we need to subtract it from our concentration up above here. Now, again, you go over to the line, you look at the best concentration, and I'm going to say that that is 0.042 molar. And again, because it's in brackets, we do not need to worry about putting that M for molarity sign. Now we can go for our time. So remember, the 0.17 was associated with this point here, furthest to the right. And I am going to say here, that this is approximately 790 seconds. Again, your estimation may be a little bit different, and I'm going to say here that this estimation for this dot, if we bring down that line, is right at 400 seconds. So to be able to calculate the instantaneous rate, we just do a very, very similar thing that we did from our values last time. So we have a negative. Very important that we do that. So we have 0.17 minus 0.042, all divided by parentheses 790 minus 400. Okay, I press enter. Again, I get all these decimals here. Okay, so I get all these decimals. In our reaction rate, it's going to start to be a lot easier to use scientific notation. And so rounding to 2 significant digits, I get a value of 6.4 times 10 to the negative 5th. So Our instantaneous rate here, our instantaneous rate is this: 6.4 times 10 to the negative fifth molar per second. Okay, so something to remember here that I really didn't mention as we were going through this. You always take the bottom point minus the top point, and then that becomes our value. So you always want the furthest in time first, subtracted by the latest in time. This would be, quote unquote, the starting of what we're trying to find. But that's how we would calculate the instantaneous rate. All right, so there's one more thing that I want to associate with kinetics, or an intro to kinetics, and what we have been doing. And it's a nice tie all together here. So we'll shift gears here, and we will go to reaction rates and how that relates to... Okay, so stoichiometry's relation to reaction rates. The first thing to note here is that stoichiometric coefficients affect the rate of the reaction. And so the easiest way to see this is through a generic equation. And so in this generic equation, we just have the coefficient A with substance A, the coefficient of B with substance B produce the coefficient D with substance D, and the coefficient E with the substance E. Now, it's very generic. Obviously, those elements do not exist, but we can use this to describe the rate in its relations to its stoichiometric coefficient. So the rate in this case would be this: the negative, because it's disappearing, 1 over the coefficient little a, or lowercase a, times the change of concentration of A, all divided by the change of time. Now that is equal to 1, and there should be negative 1 over the coefficient of B times the change in B, all divided by the change in time. Now that is equal, again, 1 over the coefficient D times the change in concentration of D over the change in time. Now, because we are starting with products, there is no negative sign. That is equal to 1 over E times the concentration of E divided by the change in concentration of time. Now, I know it's a generic equation, but it will help us on these next few problems. So we have ozone producing oxygen here in this equation. And we want to know, how is the rate at which ozone is disappearing related to the rate at which O2 is appearing? Well, the rate of the reaction can be thought of as this. The rate is going to be equal to negative, because O3 is disappearing, 1 over the stoichiometric coefficient. So the stoichiometric coefficient of ozone is 2 times the change of concentration of ozone divided by the change in time. Now this is set equal to 1, and again it's positive 1 because we're producing oxygen, 1 over the coefficient of oxygen, which is 3, times the change in concentration of O2, all divided by the change in time. And that ultimately becomes our relation between how O3 is disappearing, and how O2 is appearing. So we have an example here, and it says if the change of concentration of O2 over the change of time is appearing at 6.0 times 10 to the negative fifth molarity per second, we want to know what would the change of concentration of ozone, O3, per the change in time be disappearing at? Well, we are going to solve this, and I want to point out and help you on this particular part of this problem. For this particular problem here, the change of concentration of O2 over the change of time is given at 6.0 times 10 to the negative fifth molarity per second. Okay, I just wanted to make that clear before we go in and solve this particular example. Now, keep this in mind. We're going to shift gears to another piece of paper here, and we're going to solve this particular problem. So, just as a reminder, the rate from that first part of that problem was negative 1 over 2 times the change in O3's concentration divided by the change in time equals 1 over 3 times the change in O2 concentration divided by the change in time. Okay? And we just got done saying this, that the change in O2 concentration over the change in time is equal to 6.0 times 10 to the negative fifth molarity per seconds. Okay? So we're going to put all of this stuff into one particular problem. Our whole goal is to find out, hey, what is the change of concentration of O3 per change in time? So what I'm going to do here is I'm going to leave this the same. So I'm going to have negative 1 over 2 times the change in the concentration of O3, all divided by the change in time. This is going to be equal to 1 over 3 times, and this is where we got to be careful. Look what we have here. We can do a substitution. So instead of putting the change of concentration of O2 over the change of time, we know what that equals. So we're going to go ahead and we're going to put that in place of what we have, change of concentration of O2 over change in time. So we're going to have 6.0 times 10 to the negative fifth molarity per second. All right, so now we got to go and we have to solve it. This 1 over 2, we don't want that. The problem said, if you look back, we want the change of concentration of ozone per the change of concentration of time. So to get rid of this 2, what I'm going to do on both sides, I'm going to multiply everything by 2 over 1. Get rid of that 2. So on this side, I'm going to multiply everything by 2 over 1, or if you want to call that just 2, that's totally fine by me. So to solve this particular problem, what we're going to do is we're going to have 1 over 3. We're going to multiply that by 6.0 times 10 to the negative fifth times 2 over 1. We press enter. We get a value of 0.00004, or a lot easier to express rates in scientific notation, we get a value of 4.0 times 10 to the negative fifth m over s. Now, remember, I did not get rid of that negative sign. So this is actually negative change in O3 over change in time. And what that negative means is, hey, ozone is disappearing. Just like it said in the equation, ozone is disappearing. That's what that negative sign means. But that is equal to 4.0 times 10 to the negative fifth molarity per second. All right? So that becomes our answer. Again, all we're doing here is using stoichiometry to solve our equation. All right, so There was a lot talked about here, introducing chemical kinetics and reaction rates. I hope you have enjoyed this episode. And as always, if you have not subscribed, make sure you subscribe.